Hello, I'm a PhD student at UCL, and my talk today is based on joint work with Professor Debashish Roy from India. The essence of this work is based on rewriting an E to SD such that its solution evolves on a Riemannian manifold. When an SD models a system, the underlying dynamics often ensure that the solution evolves on a hypersurface in the space of the state variables. Developing the SD on the manifold is an expedient means to ensure that the solution remains on this hypersurface despite the freely diffusing nature of Brownian motion. In fact, controlling the noise term in the SD, which is often problematic, is the major advantage here. So there are two important aspects to this work. The first is to generalize the Laplace-Beltrami operator. I'll define this in just a minute. And the second, perhaps more important aspect is to define an energy-like term that should be minimized for the problem. This energy is then used to define the manifold. Let me start by defining the Laplace-Beltrami operator. Any given SD has a corresponding generator. It's well known that this generator for Brownian motion is the Laplacian. Similarly, when we talk of the Brownian motion on a Riemannian manifold, the corresponding generator is the Laplace-Beltrami operator, given by this equation. Here G is a metric field, and gamma is the Riemannian connection. This equation for Brownian motion is derived using the concept of stochastic development, and we use the same concept to derive the equation of a general SD on a Riemannian manifold. Equivalently, we generalize the Laplace-Beltrami operator when this original equation is a general SD. Now, before I move any further, I want to give an informal introduction to some terminology. So what is a Riemannian manifold? It's essentially a space where the notion of inner product is redefined. This makes the space generally curved, which is not true for the Euclidean space. In this setting then, the mathematical operations as we carry out in the Euclidean space are no longer going to hold, and we must switch to the analogous operations in differential geometry. The first step towards this is to attach a vector space at every point on the manifold. This brings me to the definition of tangent space. It's like it sounds, it's the vector space tangent at any point x on the manifold. This is sometimes misunderstood as Euclidean space, but that's not true. It's actually a flat Riemannian space. Now, in order to determine the derivative of one vector with respect to another on the tangent space at a given point, we need the notion of Levi-Civita or Riemannian connection. This connection is crucial while working with differential geometry, since this is where the curvature information of the manifold is captured. The next two definitions are very important for this work. So the stochastic development framework, which we are using to derive the SD on a manifold, locally establishes the relationship between the Euclidean space and this manifold M of the same dimension through an intermediate larger dimensional manifold. This intermediate manifold is a frame bundle. Its dimension is d plus d squared, where the first d components correspond to this manifold M itself, and the remaining d square components correspond to linear transformation of vectors in a tangent space. Now, since this frame bundle is a manifold, it has its own tangent space structure, which is also d plus d squared dimensional. We are interested in those d components of this tangent space which move along the manifold. They form the vector space called the horizontal frame bundle. And the remaining d square components, which can be understood as moving perpendicular to the manifold, they form the vertical frame bundle. And we are not concerned with them in this work. Moving on to stochastic development. So this WT is a path in the Euclidean space, and XT is its corresponding path on the Riemannian manifold. EIs are the standard Euclidean basis, and QTEIs are the basis for the tangent spaces at a given point on the manifold. In other words, these QTEIs form the horizontal frame bundle. They move according to the curvature of the manifold, which means they depend on the Levi-Civita connection that I described earlier. And this process of moving from the Euclidean space to its counterpart on the manifold is called the development of curves. So XT is the development of WT. And when WT is stochastic, it's called the stochastic development of curves. The final expression for the developed SD is given by equation 2 if we start with the original equation 1. I won't go into details of its derivation, but let's look at this carefully for a minute. So the original drift and diffusion terms are modified by a matrix square root of G inverse, and there's also an extra drift introduced. Notice this is the only place where the connection plays a role, and this whole term can be thought of as related to curving on the manifold upon integration. Also notice that if we substitute the metric field G as identity everywhere, which is a Euclidean metric, this connection will become 0 and we will recover the original SD. A simple pseudocode before we demonstrate the advantages of this approach for 3 different classes of problems. We start by defining an energy-like term for the given problem, which should be minimized. This should really be the takeaway from the examples, so it can be applied to other classes of stochastic systems, because this approach can be exploited essentially anywhere SDs are involved. Once we have the energy, we define the Riemannian metric and the connection from these expressions, and that's about it. We then determine the developed SD and then integrate it by any suitable integration scheme for SDs. The first example is of a Brownian motion in a potential well. The trapping of Brownian particles forms the basis of optical or acoustic quasars, and this has played a crucial role in the experimental understanding of various phenomena occurring at the molecular level, which could not have been possible with unrestricted Brownian motion. So for this problem, the expression for energy is the potential itself. We then follow the steps from the pseudocode to obtain the developed SD, which is given by 4, and then integrate it. We have the results for a 2-dimensional example where we assume a potential well around the point 1, 2. The first 2 plots are time histories of first and second components. And the one in curve in green is a standard Brownian motion, and the one in blue is by a proposed method. This is a phase plot, so it's B1 versus B2. And the last figure is just an inset from this figure. So it's this tiny blue plot here. And this shows that the Brownian motion from our method indeed stays within the potential well created around 1, 2. The next example is on the energy drift preserving integration. We consider the Duffing oscillator, and this is its equation of motion. Since B dot is not defined, we rewrite it as this system of equations. We then have the expression for the energy, which we use to define the manifold. Here, beta is just an algorithm parameter. H is the Hamiltonian of the system, which for the Duffing oscillator is given by this expression. And ZT is the mean theoretical energy, which increases linearly in time. Notice if this noise term was 0, this energy would have remained constant. And there are various symplectic integration schemes that would preserve this energy. But they do not apply for a stochastic Hamiltonian system like this one. And we show how our method can be used to design an energy preserving integration scheme for such a system. So like the previous example, once we have the expression for the energy, we follow the pseudocode and determine the developed SD for this system of equations and then integrate it. We then determine this Hamiltonian as a function of time and compare it with the mean theoretical energy. So as we can see, energy from our proposed method indeed matches the theoretical mean energy, whereas the energy from the Euler-Marama integration of the original equation grows exponentially in a very short duration of time. As a final example, we have a non-convex optimization problem. We chose the Ackley function as it's one of the benchmark problems for optimization. We treat this function itself as energy, and we solve optimization by an overdamped Langevin equation and also by the stochastically developed version of this Langevin equation, which is given by 6. These are results for a 40-dimensional problem with an ensemble size of 5. So the first figure is results by the stochastically developed equation, and this is by the original equations. And figure C is the evolution of function values with time. So this shows that the Euclidean version fails to converge for this problem. One very interesting thing to observe here is that it may seem like the overdamped Langevin equation does not do a good job of optimization, but that's not really true now, is it? All I really did with the stochastic development is change the concept of distances between points, and then the Langevin equation starts working beautifully. I will conclude with this thought. Here are a few key references, and we have a preprint of this work. There will also be a poster in the stochastic numerics session. Thank you very much.